In chapter 14, we'll talk about solutions. So, what are solutions? Let's talk about the definition of it. A solution is defined to be any homogeneous mixture. Okay, so all homogeneous mixtures can be called a solution. And in a homogeneous mixture, you'll have solute and solvent. So, let's talk about that. Solute is the substance that's being dissolved, basically something that's having a phase change usually, or the smaller component. Solvent is the thing that's dissolving, the dissolving agent, and usually the bigger part of the solution. So again, solution is a homogeneous mixture. It contains a solute and a solvent. The solute is the thing that's being dissolved or the thing that's changing its phase, or the smaller amount. Solvent is the bigger amount, and it's the thing that dissolves the solute. So the reason why we talk about the bigger amount and the smaller amount is sometimes the solute and solvent have the same phase, so you can't tell who's being dissolved and who's the dissolving agent. Then you look at the smaller component as a solute, the bigger component as a solvent. Okay, so for example, solution doesn't always just talk about solids and liquids. Sometimes we're talking about air as a solution, different kinds of mixtures of gas. Homogeneous mixtures of gas can be considered a solution as well. All right, so let's look at an example here. It says soda is a mixture of sugar and water. Which substance is the solute? In this case, sugar is dissolving in water, so water would be the solvent, sugar would be the solute. So the question is asking which substance is the solute. Our answer would be sugar. All right, next question. A solution is prepared by adding 25 ml of ethyl alcohol, which is ethanol, to 75 ml of water. So as you can see, this is a solution of alcohol and water. They're both in liquid form, but when you mix it together, the smaller component is alcohol, the bigger component is water. So the substance that is the solvent will be the bigger component, in which case water, and ethyl alcohol will be the solute. So the answer to this question where it says which one is a solvent is water. Ethyl alcohol, remember, is going to be the solute in this case. So let's look at some common types of solutions. If you have gas phase solution, you have liquid phase solution, and solid phase solution. So in gas phase solution, you have gas as a solute, solvent as a gas. So basically a mixture of different gases, and the bigger amount is the solvent. So we have air. And then in a liquid solution here, you can dissolve gas in liquid, like in carbonated drinks. You also have liquid and liquid, like ethyl alcohol and water, or antifreeze mixture here. Or you can have solid dissolved in liquid, like salt water or sugar water. We can also have solid solution where you put gas into solid, hydrogen gas in platinum solid. And then you have a solution of solid and solid, like an alloy, like brass. Homogeneous mixture of two or more components, and the ratio can be varied. So that's the one property of a true solution. Okay, so homogeneous mixture. The dissolved solute is going to be in molecule size or ionic in size, and it's going to be really, really small. And the solution can be color or colorless. Usually solutions are transparent. The solute remains dissolved and does not precipitate out of the solution over time. The solute can be separated from the solvent by physical means, usually like evaporation. When we talk about solubility, it means how much of the stuff can dissolve, how much of the solute that can be dissolved in a specific amount of solvent at a given temperature. For example, if they tell you the solubility of KBr is 27 grams of KBr for every 100 grams of water at 23 degrees Celsius. Miscible means they can mix and dissolve in each other. Two liquids can mix. Immiscible is when two liquids do not mix and do not dissolve in one another. Oil and water is immiscible. So when we talk about solubility, we have a few rules here, or sometimes you're given a chart, but here's a simple table of rules for you to remember. Every time you have sodium ion, potassium ion, or ammonium ion, it's always soluble. There are no exceptions. Anytime you have a salt made of part of this, it's always going to be soluble. Anytime you have nitrates and acetates, like sodium nitrate, potassium acetate, whatever, anything that has nitrate acetate, all of them will be always soluble. So anything paired with these guys are soluble. Now, when it's paired with Cl minus, Br minus, or I minus, like PbCl, AgCl, or BaCl2, MgCl2, whatever, anything with chlorine, bromine, iodine, the anion form of it, usually is soluble unless you pair it with silver, mercury, or lead. So in this case, if it had silver chloride, it'll be insoluble. Mercury chloride, insoluble. Lead 2 chloride, also insoluble. It's because that's one of the exceptions. Or AgI is insoluble as well, or PbI2 is insoluble. So basically, all Cl, Br, and I are soluble unless it's paired with Ag, mercury, and lead. And Ag is silver. All sulfates are usually soluble unless it's paired with barium, strontium, and lead. Okay? All ammonium and group 1 here, like we said here, this is ammonium group 1. These are always going to be soluble. So if, on the other hand, if you always assume carbonates and phosphates, oxides and sulfides are all insoluble unless paired with a group 1 or ammonium, because anything paired with group 1 and ammonium are always soluble. Okay, so you just have a few ions here with a couple exceptions, and some other ions here that are always insoluble, and a couple exceptions here. So let's take a look. Predict the solubility of barium sulfate. So according to our table, we have sulfate. Sulfate is always soluble unless paired with barium, strontium, or lead. So barium sulfate is one of the exceptions, so it will be insoluble. That means it will precipitate out in this water. All right, let's take a look at NaCl. Na is always soluble, Cl is always soluble, except paired with these guys. So NaCl, both of them points to being soluble. So silver nitrate is AgNO3. So nitrates is always soluble, and there's no exception, so silver nitrate will be soluble. Silver hydroxide. So silver hydroxide, we go to the side where we have hydroxides here. Hydroxides are usually insoluble unless it's paired with ammonium and group 1, which silver is not on that list, so silver hydroxide, it will be insoluble. Next question, ammonium carbonate. Ammonium is NH4, carbonate is CO3 2 minus, so ammonium carbonate would be NH4, and then that's plus 1, and then CO3 2 minus. So you need 2 ammoniums to 1 carbonate, so your formula is actually going to be NH4 parentheses 2 CO3. And technically we don't need the parentheses around the CO3, so we can erase that like that. Okay, so let's take a look at our chart. We have ammonium carbonate. Ammonium is always soluble, and carbonate is usually insoluble unless paired with ammonium. So because ammonium is always soluble, using anything that's paired with ammonium will always be soluble. So even ammonium carbonate will be soluble. because typically if it's any other kind of carbonate, it will be insoluble, but since it's paired with ammonium, it will be soluble. All right, so let's talk about a few things that can affect solubility. So we just talked about how polar water and oil don't mix because water is polar, oil is non-polar. So polar compounds dissolve in polar solvents. Like ethanol is polar, dissolves in water. That's also polar. Nonpolar compounds will dissolve in nonpolar solvents. Like hexanes will dissolve CCl4 because CCl4 is nonpolar. You can't mix polar and nonpolar together, but you can put polar in polar, nonpolar in nonpolar. So whenever you have an ionic compound, like a salt, dissolving in water, what actually happens is it breaks into individual ions here. Like say Cl negative is a negative charge ion. It's attracted to the positive side of the water, so the hydrogen side. And then Na plus is positive ion, so it's attracted to the negative side of the water. So you can see in the picture here. And also the explanation saying the cation, the Na plus, is attracted to the partially negative part of water, the O part, and the anion is attracted, the negative charge is attracted to the positive H plus atoms on the water molecule. So this is called an ion dipole force. All you have to remember though is the fact that sodium ion is flanked by water and is flanked by the negative side of water. Chloride ion is flanked by water, but it's flanked by the positive side of the water. And remember, on a water, you have H, H, and O. The O is the negative side, the H is the positive side. So as you increase temperature, for solids, if you warm it up, it's easier for it to dissolve. That's pretty obvious. Like if you have sugar in cold iced tea, it doesn't dissolve, but if you have sugar in hot tea, it will dissolve a lot faster. So for solids, if you increase the temperature, the solubility will increase. The gases actually have the opposite effect. So you see the pink ones are solid, it goes up if you increase the temperature. But if you increase the temperature for the gas, the solubility goes down. Why? Because as you increase the temperature for gases, it gets hotter, so there's more energy for the gas molecules. The kinetic energy goes up, which then it means it interacts less with the liquid, and it's bouncing all over the place. It's hard to dissolve it. It prefers to break free into the gas form away from the liquid. So pressure and solubility. Pressure doesn't really have an effect on solubility of liquids and solids. Unlike temperature, temperature had an effect on solids and liquids. When you warm them up, it behaved differently versus when you cool them down. But if you're talking about pressure, it doesn't do anything for solids or liquids. But if you're talking about gas solubility, the more pressure there is, the more soluble the gas will be. Okay? Just think about your soda here. When you open the bottle or the can, you hear a pop of gas fizzing coming out. That's because the can or the bottle is pressurized to hold the gas to make sure the carbon dioxide, the carbonation, stays in the liquid. And over time, the soda gets flat because the gas gets warmed up and it will release itself from the liquid, so it kind of flows off into the atmosphere. So the solubility of the gas in the liquid goes down. So bottle of root beer is under high pressure. As the bottle opens, the pressure decreases and the bubbles form, indicate gas loss from the liquid. So it's lowering the solubility of gas. So water saturated and unsaturated solution. So when you try to dissolve anything like putting sugar into water, there's some sort of a limit. Once you hit the limit of max amount of solid that you can put into your liquid, that is called the saturation level. So saturated solutions contain the max amount of dissolved solute in the solvent, the maximum capacity it can hold. Saturated solutions are dynamic. The dissolved solute is in equilibrium with the undissolved solute. So basically, it's like going back and forth, um, being dissolved versus undissolved, dissolved versus undissolved. But you can't tell a difference anymore. It looks like it stopped changing because both directions is going the same speed. So it's not saying like it stopped dissolving. It's just dissolving and undissolving, dissolving and undissolving. So it looks like it's not changing anymore. So that's when it hits a saturated limit, when you put the maximum amount of solid in there. If you haven't hit the maximum amount of solid, that means it's still unsaturated. So unsaturated solutions contain less than the maximum amount of possible dissolved solute in the solvent that you're looking at. So there's something called supersaturated solution. What are they? Supersaturated solutions contain more solute than needed to saturate a solution at a given temperature. So basically, it's holding more than it's supposed to. Saturation is where it stops taking in solute, but then you push it past the saturation limit, so it becomes supersaturated. How does that work? So if you remember, when you warm something up, the solid can dissolve better. So more solute can go on. So what you do is you keep warming up the solution, warming up the water and putting more sugar, warming up the water, putting more sugar, and then all of a sudden you take the hot pot like of water and sugar and cool it down. You take it out away from the heat. You cool it down, but the sugar is already dissolved in the water. So as you cool it down, the solution is like, hold on a second, I have way too much sugar than I'm usually supposed to at this temperature. But it became supersaturated because earlier you kept warming up the liquid so you can dissolve more and more stuff, more and more sugar, or whatever you're trying to dissolve. So if once you hit a higher level of saturation with a high temperature, you cool it down and it becomes supersaturated. It doesn't like precipitate the stuff automatically, so it just kind of stays in solution. So it's called a supersaturated solution. So these solutions though are super unstable. You just one small disturbance can cause the precipitation of solid to come out. So they'll actually crystallize. It's pretty cool. So some hot packs are releasing heat. Okay, they release heat because they crystallize the supersaturated solution of sodium acetate. So they make a supersaturated solution of sodium acetate, put it in a pack, and then any disturbance like rubbing it, squishing it will cause crystallization, and this process here will release heat, making the hot pack hot. So let's practice looking at solubility. Will a solution prepared by adding 9 grams of KCl to 20 grams of water be saturated or unsaturated at 20 degrees Celsius? So then we have to look at KCl at 20 degrees. So 20 degrees right here for KCl, let's kind of backtrack. Oh, KCl, KCl. And then we hit 20 degrees. It's somewhere around here. I would say like around 34 grams of KCl per 100 grams of water. Okay, so we know that from the table it says every time you want 100 grams of water, you can dissolve 34 grams of KCl at 20 degrees. So if you were to have only 20 grams of water, you have to make sure you divide this by 5 to get 20. So you have to divide 34 grams by 5 to see the saturation level. So the saturation level will be 6.8 grams of KCl and 20 grams of water at 20 degrees Celsius. So if you put 9 grams in there, 9 grams of KCl there would make sure you go to take all 6.8 and that would hit saturation. So it would be saturated and then the rest of them will just kind of not dissolve. Now, if you wanted to make it super saturated, you could warm it up. See, because as you warm it up, the KCl the solubility goes up. So you can warm it up to make sure all 9 goes in, and then you cool it down to 20, then it would be super saturated. But in this case, they're just asking, we're not changing the temperature, just at 20 degrees. When you put 9 grams in, it will be saturated. So let's talk about how we can dissolve solids and what type of scenarios can affect the rate. The first thing is effective particle size. The solid can only dissolve at a surface that is in contact with the solid. So the more surface that is in contact with the solvent, the better it will dissolve. So smaller crystals have a higher surface to volume area, so smaller crystals dissolve faster than larger ones. And this is pretty obvious if you have a big chunk of cube of sugar versus small little crystals of sugar. The smaller crystals would dissolve a lot faster than the big cube of sugar would. So just to show you here, if you have a small cube by 0.1 centimeters cube, the surface area of this little cube is 0.06 centimeters square. And then you have 1,000 of them in this big one. The total of the surface area for 1,000 small cubes is 60 centimeters square. But if you take a look at just one big cube here, the surface area is only 6. So you see how it's like 10 times bigger if you have a smaller cube. So again, the small cube surface area for each one, and then if you have 1,000 of them, the total is 60. Versus looking at the big guy, it's only going to be 6 times 1 squared, so just 6 centimeters squared. So how does temperature affect dissolution? So if you increase the temperature, it increases the rate of dissolution, like how much it will dissolve. Okay, for solids, yes, increase the temperature, solubility will go up because it increases the rate of dissolution. Why? Because when you give them more temperature, they hit the solid surface more often. The solvent and solid meet more often so they can dissolve more rapidly because there's more interactions here. The solid molecules are more easily separated from the solid due to higher kinetic energy. So more energy, easier to dissolve. Increasing temperature increases the rate of dissolution. So the effect of solute concentration on the rate of dissolution, the more solute you have, the higher the rate of dissolution will be. Just because there's more solute to dissolve, they can go faster. But if you have a lower amount of solute, you'll have a lower rate of dissolution. Now, one thing to watch out for though, as you dissolve your stuff, it's going to be pretty fast in the beginning. Once it gets close to the saturation level, it starts to slow down in dissolution. When you stir a solution or agitate a solution by stirring, you break up the solid into smaller pieces, increasing the surface area, thereby increasing the rate of dissolution. So solutions are a good reaction medium. For example, if you have just solid KCl and solid silver nitrate, it's not going to be able to react on its own. But if you put KCl into water and AgNO3 into water, they're both soluble aqueous solutions. You can actually make a reaction happen by forming precipitate of silver chloride and aqueous solution of potassium nitrate. So if you break them apart into ion, this is a complete ionic equation where you write K as K plus, Cl as Cl minus. So these are in ionic aqueous form. Same for silver nitrate, silver ion, nitrate ion. And then AgCl solid is the precipitation, so we write it as a compound. And then you have K plus aqueous potassium ion and nitrate ion right here, both are in aqueous form. If you notice, potassium nitrate stays the same. These guys are called the spectator ions. Okay, spectator ions are removed and you have the net ionic equation. So ion plus ion equals to solid compound. So remember, complete ionic equation is where you break everything into ions and you write the precipitation or the compound that precipitates in one compound unit. Everybody else will be in ionic form. Net ionic equation is just a complete ionic equation minus the spectator ions, and you have the leftover called net ionic equation. So we want to talk about different ways of expressing concentration solutions. We have dilute solution. That means it's small amounts of solute in it. So like 0.1 molarity of HCl is dilute hydrochloric acid. If it's concentrated, it has a lot of solute in there. So like for example, 12 molar HCl solution is concentrated acid. So 12 molar versus zero point 0.1, 12 is considered concentrated, 0.1 is considered dilute. Let's take a closer look at different units that we can use for talking about concentration of solutions. The first one is mass percent. We've talked about this before. Mass percent is mass of what you're interested in over mass of everybody times 100. So if you apply it to a solution, you take mass of solute over mass of solution, which means solution is the addition of solute and solvent. So mass of solute divided by mass of solute plus solvent times 100 will give you mass percent. If you want parts per million mass, then you take the mass of solute divided by the mass of solution, which is the solute plus solvent, times a million, and you get ppm, parts per million. There's also a unit called ppb, parts per billion, and you just times by a billion, which is 3 extra zeros. Now, let's talk about mass over volume percent. That means you just have mass on the top, volume on the bottom. So mass of solute on the top, milliliters of solution on the bottom times 100. That will give you mass volume percent. Now, the next part is if you want to do just volume percent, you do volume and volume. So mils of solute divided by mils of solute and solvent, which is mils of solution, times 100 will give you volume percent. So there's different kinds of percent: mass volume percent, and volume percent. So just by the name, mass means everybody is mass volume, or volume percent. Molarity is something we will be using a lot. The symbol for molarity is capital M, and we moles of solute divided by liters of solution. Okay, so you want to make sure you memorize these units here. Molality is something you'll learn later on. We'll be using that for calculations later. The symbol for molality is little m, and it's moles of solute divided by kilograms of just the solvent on the bottom. So this is unique and special because everybody else has solutions on the bottom except for molality. So far, all the calculations that you'll be using will not have the molality just yet. This will be used in other later parts and later classes. Calculate the mass percent of NaCl in a solution prepared by dissolving 50 grams of NaCl in 150 grams of water. So mass percent is mass of solute, which is NaCl, divided by mass of the solution, which is NaCl plus water. So 50 grams of NaCl and 150 grams of water gives me 200 grams total of the solution. Okay? So I know what I have now, and I need to take the solute divided by the solution times 100 to give me the mass percent. So that would be 50 grams of NaCl divided by 200 grams of solution times 100, which means it's 25% by mass percent of NaCl. When you say 25% NaCl by mass, that means every time you have 100 grams of solution, you will have 25 grams of NaCl. What is the mass of Na2CO3 sodium carbonate needed to make 350 grams of a 12.3% aqueous solution? So 12.3% means you have 12.3 grams of solute in every 100 grams of solution. We know we have 350 grams of solution here. So if you know you have 350 grams of solution, you can use the fact that you know that 12.3 means 12.3 grams of the solute here, and then in every 100 grams of the solution. Okay, so one way to do it is you just put the formulas together, but I wanted to also write this out. If you write down 12.3%, this means you can find 12.3 grams of sodium carbonate or the solute, we just write solute, and then you will find this in 100 grams of solution. Okay, so 12.3 grams of solute, 100 grams of solution, and we know we have 350 grams of solution. So 350 grams of solution, and I have 100 grams of solution to every 12.3 grams of solute. And I can get the grams of solute here, which is sodium carbonate. So you'll get the same answer, and it will be 43.1 grams. So if you take a look at the example here, they combine these two formulas here, and they told you just move stuff around. So mass of solute is divided by mass of solution times 100, and mass percent is given there. So you rearrange your formula here. You put your mass of solute on one side, you end up getting mass percent times mass of solution divided by 100, and you put the formula in that way. So you can do that, or you can know that if it means 12.3 grams per 100 grams of solution, the calculation is exactly the same, you get the same answer. So the next question is a mass volume percent. Saline is 0.9 mass per volume percent NaCl solution. What mass of sodium chloride is needed to make 50 mils of saline? So what we know is we have 50 mils of saline, and we also know the mass volume percent there. So again, we can use the formula. We just rearrange it, okay? So you have mass volume here, grams per milliliter, so grams of solute per milliliters of solution, and we know we have 50 mils of solution, and we want to rearrange, and we know this is also 0.9 here, and we can rearrange the formula to get mass of solute, which is grams of solute, equals to the mass volume percent times milliliters of solution divided by 100, and you will end up getting, plugging in 50 mils times 0.9, and then 50 mils of solution times 0.9 mass volume percent divided by 100, you get 0.45 grams NaCl. So you just have to rearrange the formula here, or you can remember that this here means that you have 0.9 grams in 1 milliliter of solution. And you'll see that it gives you the same type of calculation. And we have 50 mils. Not 1 mil, 100 mils. Let's do 100. Erased. Right here. And if you do that, you literally get the same formula, because you see 50 mils of solution, and you have 100 mils of solution, and 0.9 grams. And you get the same answer. So let's try another mass volume percent question. So this is 3% mass volume of hydrogen peroxide, okay? Well, volume of 3% mass volume percent hydrogen peroxide solution will contain 10 grams of hydrogen peroxide. So what you're looking for is 10 grams of hydrogen peroxide, and you want to turn it into volume. And you also know the ratio, which is 3 grams of H2O2 that can be found in 100 mils of solution. Okay? And you know that you want 10 grams. Well, 10.0 grams. So then you look and you do 3 grams of H2O2 can be found in 100 mils of solution. Okay? So that should give you an answer of 310 10 times 333.33. It keeps going forever. Now, we only have 3 sig figs though, and actually just 2 sig figs because of this 2 here, and there's 3 sig figs. So we want to stop our answer at the second sig fig. So it will be 330 mils. Okay? Or we can say 3.3 times 10 to the power of 2 mils. Now, obviously, that's one way to do it. The other way, remember, we just rearranged the formula of the solution. So we know that our 10 grams is what we want, and we also know it's 3 grams per volume percent. So mass per volume percent is grams per mils times 100. So it's grams over here. And then you want to go ahead and rearrange it. You want to look for volume solution. So volume solution is rearranged to be grams of solute divided by the mass volume percent times 100. So again, to solve for it, this is volume solution. So mass of solution would be 10 grams of solute divided by 3.0 mass volume percent times 100. You get 330. Same answer. So let's try some more volume percent. What volume of beer that is 6% by volume alcohol contain 200 ml of ethanol? So ethanol is the alcohol, okay? So they want you to calculate how much volume of beer will contain 200 mils of ethanol. So in this case here, this is actually volume percent, not mass percent. So it's volume over volume, okay? So when you see this number here, you can do like what we just wrote. 6% means every time you have 6 mils of alcohol, you can find this in 100 mils of the alcohol. Okay, so then if they want you to find how much, what volume of the beer will contain 200 ml of alcohol, you know that the alcohol, this is solution, okay? So we should call this beer. Okay, and then you know that 6 mils of alcohol is in 100 mils of beer. So that should give you an answer of 3,333, but since we're just at 2 sig figs, it will be like 3,300. So let's just put that as 3,300 ml of beer. Now, we can also do it by just rearranging the formula. You know the formula is volume of solid or volume of solution. And if you want the volume of beer, which is the solution, you rearrange it. So volume of solution is volume solid divided by volume percent times 100. So you just put your numbers in. 200 mils of your solid, which is the alcohol, and then 6% volume times 100. You get 3,300 mils, not soda, it's actually beer. Okay, so you get the same answer either way. And really the formula is about the same, so whichever you prefer. So let's practice another one. This is again volume percent. The question is, solution is prepared by mixing 220 mils of propanol with enough water to produce 400 mils of solution. What is the volume percent of propanol? So it'll be 20 mils of propanol on the top, and then the total volume of solution is 400 mils, so it'll be 20 over 400 times 100. That will give us 5%. So the next thing we want to talk about is the unit molarity. Molarity is capital M, and the unit is moles of solute per liter of solution. So remember, it's capital M. All right, so let's talk a little bit more about molarity. We can use it to calculate concentration, obviously. And if you want to see an example, if you want to prepare 1 molarity KCl solution, you must have 1 mole KCl dissolved in 1 liter of solution. We will use a volumetric flask where there's a mark right there on a volumetric flask. If your lower meniscus of the water hits that number, it will be exactly 1 liter. And if you weigh out certain amount of grams, 1 mole of KCl there, and you can make a 1 molarity solution of KCl. So let's calculate molarity here. Calculate the molarity of a solution prepared by dissolving 9.35 grams of KCl in enough water to prepare 250 ml of the solution. So molarity is moles of solute divided by liters of solution. So you must take this grams to moles because this is a solute, and our volume here must be turned to liter. So what we have here is going to be 9.35 grams divided by 74.551 grams of KCl to give me the moles of KCl. And I also have to change the volume to liters, so it's 0.250 liters. So molarity is the number of moles of KCl divided by the liter solution. I get 0.502 molarity KCl. So capital M stands for molarity. So let's try another molarity question. How many grams of KOH is required to prepare 600 ml of a 0.450 molarity KOH solution? So what you want to do is go ahead and recognize that 600 ml is going to be really just 0.6000 liter, correct? But if you don't remember this, you just need to remember the conversion that 1 liter 1 liter is 1,000 mils. Okay. We also know the conversion of 0.450 molarity means 0.450 moles of KOH found in 1 liter of solution. So these are my solution here. Okay. So what I would do is I can start by saying, well, I know I have 600 mils. Okay, of solution. And I know that every time I have 1 liter of solution, it really means 1,000 mils of solution. So you see how I cancel out the mils of solution there? Okay. Now the next thing we go ahead and do is we want to go ahead and add the molarity in. So 1 liter goes on the bottom, but the molarity is 0.450 moles. Okay, so now I'm crossing off the liters of solution. My answer is moles of KOH, but I really need grams of KOH. So you know that the molar mass KOH is 1 mole of KOH weighs 56.11 grams. And that should give us our answer once you calculate that. Okay, so let's see what we get. And you should get like 15.1 grams. Now, so that's one way to do it. If you forget your formulas, you can just use dimensional analysis. You can also remember that if molarity is moles of solute per liter as a solution, moles of solute is molarity times liters. So then you have to remember that you can get the moles of KOH by going ahead and calculating 0.6 liter times the molarity, right? So you have your molarity right there times the 0.6 liter, you get the moles of KOH, and then you just use the molar mass to convert that moles to grams. I guess I should erase this top part here so you can see. But we get the same answer. Okay? Alright. So those are 2 ways to get your answer, and both of them give you the same answer for D. Next, we want to add molarity into our stoichiometry problems. So how many mils of 0.175 molarity HgNO32 are needed to not precipitate but react with 2.5 grams of Ki? So here's our balanced equation. You can see the mole-to-mole ratio of HgNO32 to Ki as 1 to 2. So you're going to use that. So before this, usually they give us grams of something. You do the mole-to-mole ratio, and then you turn it back to grams. But right now, we're going to go a different level here. We're going to use molarity and calculate volume here. Okay, so we want to start with you never start with molarity because molarity has two parts to it. So like, how do I know two parts? This means it's 0.175 moles of HgNO3 2 in 1 liter of solution. So I can know that I don't want to start with this. I'm going to start with 2.5 grams. Okay, so if I were to start with 2.5 grams, I can say, well, I know I have 2.5 grams. Let's write it over here. Okay, Ki. I'm going to turn this into moles of Ki, and then I'll do the mole-to-mole ratio to get to moles of HgNO3 2, and then I'll use molarity to get 2 liters of HgNO3 2, and then I'll turn it to milliliters, okay, of HgNO3 2. So that's what we want to do. We want to go from grams to moles, do the mole-to-mole ratio, which is 2 to 1, and then you turn the volume to milliliters. Remember, 1 liter is 1,000 milliliters. So what we want to do is start with 2.5 grams, turn it into moles by using molar mass. So cancel off the grams of Ki. Now I have moles of Ki. I know it's 2 moles of Ki to 1 mole of HgNO3 2. So we cancel off the Ki here. And then we do that molarity here. See? 1 mole, 0.175 moles in 1 liter. So right here. So you can write liters here and then go to milliliters, or you can just straight up put 1,000 mils here. It's 0.175 moles of HgNO3 2 to 1,000 mils, and you get your answer in mils. If you straight up use the molarity, it's 1 liter here, remember? Then you just turn the liters to milliliters. Same answer. So we get our answer as 43 mils. So here's another stoichiometry example. How many grams of AgCl will form by adding enough AgNO3 to react fully with 1500 mils of 0.400 molarity BaCl2 solution? So what you're comparing is BaCl2 solution to get the product AgCl2, and you know the mole ratio is 1 to 2. So what you want to do is remember you have 0.4 molarity, so always remember if you have 0.4 molarity, write this down. That means it's 0.400 moles of BaCl2 that can be found in 1 liter of BaCl2 solution. Okay, let's write that liter. Okay, so then you'll take the 1500 mils of BaCl2, turn it into liters of BaCl2, and then we'll use the molarity term here right above this guy here. We're going to use that to translate this into moles of BaCl2. And then we'll do the mole-to-mole ratio. The mole-to-mole ratio is 2 moles of BaCl2 to 1 mole. 1 mole of BaCl2 to 2 moles of AgCl. You get it to go to moles of AgCl. Okay? And then you just use the molar mass to turn to grams of AgCl. So there's a lot of steps here, but it's good to kind of draw a pattern. So that's what we want. We want to go from the volume of BaCl2 to moles of BaCl2. This will go using the molarity, mole-to-mole ratio, and then molar mass to get to the grams. So in this case, you start with 1500 mils, 0.4 moles per 1,000 mils, or you just put 1 liter and change this to liter first. And then you have the mole-to-mole ratio, 1 BaCl to 2 moles of AgCl. See how you cross up the mils and the BaCl here, and then you cross up the AgCl. Now you have grams of AgCl. The answer is 172. Last thing we want to learn about solution is we want to talk about dilution. Dilution is by adding a solvent to a concentrated solution to make the solution less concentrated, more dilute. Okay, so just when the solution is diluted, only the volume changes. The number of moles of solute stays the same because you're not adding solute, you're just adding the solvent, like adding more water to make it more diluted. Okay, so the moles before dilution, moles after is always the same. So because we know that molarity times volume gives me moles, I can write a formula M1V1 equals M2V2, where molarity times volume of the first scenario equals to molarity times volume of the second scenario, because I know the moles is the same. So we'll be using this formula a lot, okay? So a dilution practice question we have is going to be, what volume of 12 molar HCl is needed to make 500 mils of 0.1 molar HCl? So this is going to be my original molarity. So this is M1. So this is the second V1. And then this is the second solution here. This is M2. This is V2. Okay, and then you just know we assign M1, V1, M2, V2. And then we solve for V2. So V2 will be we solve for V1, not V2. And then it will be V2 times M2 divided by M1. You just plug the numbers in, you get the answer 4.2. So one last problem here. Calculate the molarity of NaOH solution right here, prepared by mixing 100 mils of 0.2 molarity NaOH with 150 mils of water. So you originally have 100 mils of a 0.2 solution. You're going to add 150 mils of water. So your new volume is going to be 150 mils and 100 mils added together, correct? So that's my V2. My volume 2 is going to be 250 mils. Okay? My molarity 2 is what we're looking for because we don't know. But I do know my molarity 1 is 0.2, and my volume 1 originally is 100 mils. So all we do is we just go ahead and use M1V1, M2V2. And we are going to solve for M2. So I'll just rearrange it right now. M2 is M1V1 divided by V2. So let's go ahead and put the numbers in. It's 0.2 times 100 divided by 250. So when you do that, M2 equals to 0.080 molarity. And that's the end of our chapter for solution.